Let's wrap up sections 7.1 and 7.2. Once you've completed 7.1 and 7.2, you should be able to identify whether a study has used independent groups, paired with repeated measures, or paired with matching design, and complete a simulation-based test of significance for a paired design by writing out the hypotheses, determining the observed statistic, describing how the null distribution would be created, computing a p-value, and writing out an appropriate conclusion and interpretation of that p-value, which would include scope of inference. Let's use the example from your book in section 7.2. Imagine you've hit a line drive and you're trying to reach second base. What path should you take? Does the path you take to round first base make much of a difference? You can either take a narrow angle, which takes you tight to the baselines, or you can get out wide before first base to round more quickly. We will call these the narrow and wide angle paths. In 1970, Woodward investigated these base running strategies to see which was faster. 22 different runners were timed from a spot 35 feet past home to a spot 15 feet before second base. Each runner would use each strategy, with a rest in between, and we randomly decided which path would be run first. So what type of design is this? Paired design with repeated measures, because each observational unit was measured twice. That pairing controlled for the runner-to-runner variability in times. For each runner, we would need to record the base running method, wide or narrow, which is categorical, and that will be helping to explain the response variable, the running time from home plate to second base, which is quantitative. I would guess that's measured in seconds, but we don't know for sure based on the information given thus far. Is this an observational study or an experiment? Well, since we randomly assigned the method of the runner and which would be done first, it's a randomized experiment. And then again, the type of study design paired with repeated measures, as discussed on the previous slide. Here are the results of the study. You see a table which displays the first 10 runners' narrow angle and wide angle times, as well as a dot plot for the times of each of our 22 runners on the narrow and wide path. Based on this dot plot, does there appear to be a path that is faster than the other? It's tough to tell, or not really. There's a lot of variability in the running times within each path, and the two distributions overlap a lot, so it does not appear that the mean running time of the two paths are different. However, we should not be analyzing a difference in means because this data is paired. We should be thinking about the differences in times for each of the 22 runners instead. Here, we've added a table that displays the differences for each runner, and now we have a dot plot of the differences in times for each runner, using narrow path minus wide path as the order of subtraction. Based on this dot plot, does there appear to be a path that is faster than the other? Yes. We can see a majority of the differences are greater than 0, indicating that the narrow path had a higher time, i.e. was slower, than the wide path on average. We see that the mean of differences, x bar d, is 0.075 seconds, with a standard deviation of the differences, s sub d, of 0.0883 seconds. Let's look at those original dot plots one more time for the narrow and wide angle paths, but now we'll use a line to connect observations on the narrow and wide angle. What do you notice about this dot plot? Well, most of the lines slant in the same direction, forward or with a positive slope, indicating again that the narrow path on top was larger or slower than the wide angle path on bottom. What is our parameter of interest in this study? Paired data uses mu sub d as the parameter of interest, which is the long-run mean difference, in this case, in running times, for runners using a narrow angle path instead of a wide angle path, narrow minus wide. Note here that we still need to give the order of subtraction in order to understand what these differences are representing. How about the null and alternative hypothesis? Our null hypothesis will always be that the mean of the differences is 0, or in the long run, the difference in running times for each person will be 0 on average. The alternative hypothesis is that mu d is not equal to 0, because we're just looking for which running path is going to be faster, and we didn't have an idea about that at the start of the study. In other words, the long-run difference in running times for each individual is not 0 on average. How can we use simulation-based methods to find an approximate p-value? The null hypothesis basically says that the running path doesn't matter, so we can use our same set of data and for each runner, randomly decide which time goes with the narrow path and which time goes with the wide path, then compute the difference. We can randomly assign those using a coin toss. If the coin toss comes up heads, we will switch the observations, so we will flip-flop which observation went with which angle. That changes the sign of the difference, and so I would move the difference to the opposite side of 0. Notice that we're not breaking up our pairs, we're just flip-flopping which observation or which running time went with which path. After we flip these coins for each runners and compute the differences for each of them, we will then find the mean difference. From our simulation, the mean of the new set of differences is 0.016. That is certainly less extreme than the observed mean difference of 0.075, which is what we would expect. Finally, simulations, we did not get any values that were as extreme as our observed mean difference of 0.075. Let's create more than 26 repetitions though. Here's a null distribution of 1,000 simulated mean differences. Where is it centered? Around 0. The mean of the distribution is 0.001. That makes sense because we assumed that the average difference was 0 in the population to create this simulated distribution. And where does our observed statistic of 0.075 fall? Pretty far out in the tails. Notice that the label on the x-axis only goes out to 0.06. In fact, only one of the 1,000 simulated repetitions of random swappings gave a mean difference value at least as extreme as 0.075. Notice to get our p-value, we selected beyond because this was a two-sided alternative, and then beyond our observed mean difference of 0.075. With a p-value of 0.001, we can state that there is a 0.1% chance of observing a mean difference in running times between the narrow and wide paths of 0.075, or something further from 0, if we assume that running path does not matter and that the true mean difference in running times between the narrow and wide angle paths are the same. We can conclude that there is very strong evidence against the null hypothesis, and therefore state that the running path does matter, with the wide angle path being faster than the narrow angle path on average. We can draw a cause and effect conclusion here since we used a randomized experiment where we have randomized the order of the running methods for each runner. There was not a lot of information about how these 22 runners were selected, so it would be difficult to decide whether to generalize to a larger population or not. To be on the safe side, we should just say these results apply to runners similar to the 22 who were in our sample.